Transformations of logarithmic functions. In this video, you are going to explore the characteristics that can change the shape and size of an exponential and logarithmic function. Let's take a look at how transformations can be applied to a logarithmic function. Let's start by graphing the function y equals log x minus 2 minus 5. We want to state the key features of the function, the domain and range, the x-intercept if it exists, the y-intercept if it exists, and the equation of the asymptote. To do that, we'll do this sample problem. Graph the function y equals log x minus 2 minus 5. State the key features of the function, the domain and range, the x-intercept if it exists, the y-intercept if it exists, and the equation of the asymptote. To do that, start by graphing y equals log x, and that's shown on my graph in green. The graph y equals log x minus 2 I've shown in aqua. You will see by my red arrow that it's a 2 unit to the right horizontal translation. Now I will add the -5. So the equation becomes y equals log x minus 2 minus 5. This is a 5 unit down vertical translation. So from the aqua, I come down 5 units. Now, the domain, x is an element of the real numbers, and from the graph we can see that x is greater than 2. The range, y is an element of the real numbers. To find the x-intercept, set y to 0. Y equals log x minus 2 minus 5 is our equation. Y is 0, and that becomes log x minus 2 minus 5. Move the -5 to the left. So 5 is log x minus 2. Take the log out by making the base 10 and adding 5 as the exponent. So that's equal to x minus 2. Move the -2 to the left to isolate x. So 10 to the exponent 5 plus 2 is x. Now that gives us that x is equal to 100,002, which is 100,002. So the y-intercept occurs when x is 0. So y equals log x minus 2 minus 5, set x to 0. So y is log -2 minus 5. However, the log of -2 is undefined. This means there is no y-intercept. So the vertical asymptote occurs when x minus 2 is 0. And so the vertical asymptote is x equal to 2. Now we want to sketch a graph of each function. Y equals 5 log x plus 3, and then y equals log negative 2x plus 4. To do that, we need to start by identifying the key features of each function. But note, when applying multiple transformations like we're doing in these two questions, it can be helpful to focus on certain anchor points such as 1, 0 and 10, 1, as well as the position of the asymptote. So we're off. Sketch a graph of each function. Start by drawing y equals log x and then y equals 5 log x. Check your points. 1, 0 became 1, 0, didn't change. 10, 1 becomes 10, 5. Now apply the horizontal shift, which is x plus 3. So what happens to our anchor points? When we have a vertical point and a vertical asymptote, they'll both shift 3 units to the left. So 1, 0 becomes negative 2, 0. Now we're looking at our blue graph, and 10, 5 becomes 7, 5. One was horizontal, one was vertical. Next one, log negative 2x plus 4. So the negative 2 reflects horizontally in the y-axis, and the plus 4 translates up 4 units. The graph of this function can be the graph of this function can be obtained by applying a horizontal compression and a horizontal reflection and a vertical translation of the graph. Now remember, when it's inside the bracket, it has to change from a 2 to a 1/2. So 1, 0 shifted to 0.5 and 2. 10, 1 shifted to 5 and 1. Now I have little squares to show that if you want to stop the slideshow. Okay, now we're going to do the reflection. So 0, 5, 0 translates a reflection to negative 0.5 and 2. 5, 1 translates to negative 5 and 1. Again, follow my little squares and you will see these values. Apply the vertical translation, log negative 2x. And we're going to add a plus 4. Y equals log negative 2x plus 4. Now our points, 0.5 and 0, will change to negative 0.54. So now we've gone up vertically. Negative 5, 1 translates to negative 5, 5. Again, watch my little squares. So here is an example. So for the function y equals 5 log x plus 3, the domain, x is an element of the real numbers and x is greater than negative 3 from inside the bracket. The range, y is an element of the real numbers. To find the x-intercept, we know that y is 0. So we take our equation, we set y to 0, and we get 0 equals log x plus 3. Now, to take out the log, remember, 10 to the 0 is x plus 3. 10 to the 0 is 1. So y equals x plus 3. Then we have negative 2 is x. So this means our x-intercept is negative 2. We confirm looking at a graph, yes, that is true. So now onward to the y-intercept, and we set x to 0. We get equals 5 log 3. To calculate that, we use our calculator, and we get 2.386. So the vertical asymptote is at x equals negative 3. We round it. Okay, one more quick one. For the function of y equals log negative 2x plus 4, the domain x is an element of the real numbers, x is less than 0, and the range y is an element of R. Start again by finding your x-intercept, and we find there that the x-intercept is 10 to the negative 4 equals 2x, and that simplifies to negative 1/2 times 10 to the negative 4, which works out to be negative 0.00005, and that is our x-intercept. Now we find the y-intercept, log negative 2x plus 4, log negative 2 times 0 plus 4, so our answer is 4. So let's summarize. This I would add to my journal, my manual of key pieces of information, so you need this for the exam. So log x plus c, c translates up if it's greater than 0, translates down if it's less than 0. Now it's inside the bracket, x minus d. So if d is greater than 0, it translates to the right. If it's less than 0, it translates to the left. The a in front, it says stretch vertically by a factor of the absolute value of a if a is greater than 1. And it compresses vertically by a factor of absolute value a if absolute value a is less than 1, and it reflects if a is less than 0. Then we have the log of kx compressed horizontally by a factor of 1 over k if k is greater than 1, and it's stretched by a factor of 1 over k if k is less than 1 and does not equal 0. Now this is somewhat similar to what we started with, trigonometry. So, what's our steps? Ensure the function is in the form a log k x minus d plus c. Apply horizontal, vertical stretches, apply reflections, and then horizontal and vertical translations.